Hello and welcome. This is the Chapter 6 summary. One of the main topics in Chapter 6 was the hydrogen emission spectrum. This was following the discussion of light, how we saw light is a wave that also behaves like a particle. We can think about photons and their relative energy as a function of their frequency or their wavelength. And we can then see that a gas sample that was struck with a high voltage of electricity causing a light to be given off, that the light could be separated into individual wavelengths coming from four distinct transitions. And so the H-atom emission spectrum was discovered a little bit before the discovery of the electron, about 10 years or so before the discovery of the electron. They were able to work out an equation that related the wavelength to a constant that could be multiplied by two whole numbers, an n1 and an n2. Niels Bohr provided some explanation for why this equation worked about 20 years later. So it's actually maybe more like 30 years later, but Niels Bohr sort of looked at Planck's assumption of light, sort of that the wavelengths of light here are just related to the energy differences of the transitions that were arising to that light being given off, so that you could imagine perhaps we have excited energy levels and they could be decaying or returning back to some lower energy level, and then each of those transitions has a different amount of energy. And so then perhaps these energy levels were related to discrete orbits of certain radii around the nucleus. You might imagine the nucleus of the hydrogen, electrons, according to this model, orbiting the nucleus. Current models would actually say a better way of thinking this electron is more like a standing wave spinning around the charge, as opposed to an actual discrete particle that's actually orbiting around the nucleus. So almost like a continuous wave, if you will, is a better description of what these energy levels are corresponding to, but that a discrete amount of energy is required to change those energy levels. If we want to go up, if we want to go from n equals 2, say, up to n equals 4, then that atom has to absorb energy for that transition to take place. Then if we have n equals 4 returning back to, say, n equals 2, then energy can be emitted. And as energy is emitted, perhaps that energy goes into creating a photon of light that's given off, and perhaps a photon of light could be absorbed in by the lower state to cause the energy of the atom to be increased by increasing the energy level. So only orbits of certain radii, according to this model, are permitted for the H-atom. The lowest energy state possible is n equals 1, so there's no energy state lower than n equals 1. Energy is emitted or absorbed as the electron changes from one energy state to another. This energy is related to h nu. Some sort of typo here. But so the energy emitted or absorbed is related to h nu and the energy change required for the atom. So what do the values mean for the Bohr model? So the Bohr model just means our ground state, higher energy states. If we have higher energy states that are populated, then they can decay back towards the ground state. And then the question is how much energy is emitted by those particular transitions. So as we go down, energy is being emitted by the H-atom, perhaps in the form of light being given off. And then as we go up, energy would have to be absorbed, perhaps by wavelengths of light being absorbed in by the atom, or perhaps by some other form of energy being absorbed, like electrical energy. So you can look at the delta E. For the H-atom, if delta E is positive, then energy must be absorbed for that transition to occur. A photon in this instance is possibly absorbed. So NF greater than NI. If your final state's higher than your lower state, then energy has to be absorbed to go upward. And negative delta E implies energy is being released to create the photon of light that you might observe. So some important ideas to point out for the Bohr model that are not particularly addressed by this model, as electrons exist only in certain discrete energy levels, which are described by quantum numbers, is one important sort of note from this model, that we're getting this idea of energy levels and quantized energy levels from the Bohr model. Energy is involved in the transition of an electron from one energy level to another. That's a helpful concept to make sense of, that as we're changing energy levels for the H-atom, that different energies correspond to those changes in energy level. If we want to go to some higher energy level, energy has to be absorbed. But the limitation here is this only works for hydrogen. It can't really apply to other other atoms. So this isn't going to work well if we try to apply it to helium, lithium, beryllium, or even larger atoms than that. We might be able to apply this model to other 1-electron ions, like helium plus, lithium 2 plus, beryllium 3 plus, but those ions are very rare and not particularly useful. So the utility, the application of this model is limited to just being able to describe hydrogen, but it allows us to maybe start looking for other ways to describe the configurations of other atoms through perhaps a ground state electron configuration and thinking about the orbitals that are involved in these types of atoms. So we end up talking about quantum numbers to describe the different types of orbital sets that we might imagine there being for larger atoms, for their electrons to distribute into. These orbitals describe a spatial distribution of the probability of electron density. So we're just trying to figure out where do you expect to find electron density around atoms. And then the orbitals are described by a set of 3 quantum numbers. We're going to see, or we've seen in class already, that the orbitals that describe a particular, or the quantum numbers that describe a particular orbital are the n value, the L value, and the m sub L. And then once you factor in that each of the orbitals can have a spin up electron or a spin down electron, so they can have an m sub s value of plus 1/2 or minus 1/2. And the one weird thing being when you draw this diagram, you don't necessarily mean the up is plus 1/2, down is a minus 1/2. Just one of them is the one spin, the other is the opposite spin. But that each electron, each orbital can contain a maximum of 2 electrons. Therefore, each must have opposite spin within any one particular orbital. So this leads to for the first few values of n, working out that when n is equal to 0, that is describing a 1s orbital because the only possible value of L is 0. L is telling us about the shape of the orbital. N is telling us about the size. The m sub L is telling us about the orientation or the direction of the orbital. And then the number of m sub L's are telling us the number of orbitals that are possible within the subshell. And so if we look at n equals 2, then the range of L values goes up to n minus 1. So we have a 0 or a 1 for L. The 0 is describing the 2s subshell, and the 1 is describing the 2p subshell. So the L value of 0 defines an S shape, 1 a P shape, 2 a D shape, 3 an F shape. So if we look at the 2p subshell, the range of m sub L goes from the minus L to plus L. So we get 3 different values of m sub L, so we get 3 different orientations for that orbital. We can have the orbital pointing on one axis, on the opposite axis, or coming right out at us. So that's describing the orientation or the direction of the orbital. 3 of those orbitals gives us a total of 4 within the n equals 2 shell. So a shell describes the n value. A subshell describes the n and L value. So like a 2p is a subshell that's comprised of 3 orbitals. The n equals 3 shell is comprised of the 3s, the 3p, the 3d subshells, of which there's 1, 3, and 5 orbitals respectively. So that's a total of 9 within the entire subshell. So you're going to get 18 electrons within the n equals 3 shell, but only 8 electrons within the n equals 2 shell, and then of course only 2 electrons within the n equals 1 shell. And as soon as you get to 4, you just pick up having the 4f subshell, of which there's 7 orbitals that are possible, and that gives us a total of 16 orbitals within the entire n equals 4 shell. So again, the spin is describing within an orbital. You can maybe picture that the electrons are standing waves spinning around a nuclei, one direction or the opposite direction. And so the spin can be either plus or minus 1/2. The orbital energies, we can maybe understand them from a diagram like this one, where we're just looking at the lowest energy being the 1s, then of course a 2s is going to be higher, then a 3s, then a 4s, but then our p kind of fit in, 2s to 2p, then we go to 3s in terms of energy, then the 3p, then the 4s, then the 3d, then the 4p. Now, you may find a diagram like this hard to interpret in terms of how you're supposed to memorize this, but if you look at a periodic table, as we'll look at in a few slides, you'll see that this is the order of which the elements go in terms of the order of them filling in their last electrons. So we can get the relative orbital energies just by inspecting and then looking at a periodic table. So Pauli exclusion principle, no 2 electrons in the same atom can have the same set of 4 quantum numbers. If that were the case, then those electrons would be occupying the exact same space. So no two electrons in an atom could have the exact same energy, and no two electrons can occupy the exact same space at the exact same time. So this means that every electron in an atom must have at least one of the four quantum numbers different from each other. So they each have to have their own n, l, m sub l, and m sub s value. So Hunds' rule says when filling degenerate orbitals, that means orbitals that are equal in energy, the lowest energy is attained when the number of electrons having the same spin is maximized. So this is best explained if we think about going from lithium to beryllium, perhaps. So that's going from a 2s1, let me zoom in a little bit on this. So that's going from a 2s1 to a 2s2, so we just have one unpaired electron for lithium, two for beryllium. And as we go from boron, carbon, nitrogen, to neon. So if we just look at the boron, carbon, nitrogen, this is going from a 2p1, 2p2, and a 2p3. So we're filling into the 2p subshell. So we have three 2p orbitals that are all equal in energy to each other. So that's what we mean by saying that these orbitals are degenerate in energy. So since the 2p set of orbitals are equal in energy, then we're going to fill the electrons in from one orbital to the next to the third, maximizing the spin of all three electrons. So we end up with a net spin of three electrons in the same direction. So nitrogen would have the greatest spin, if you will. It would have the greatest ability to be pulled into a magnetic field because it has the most spin compared to, say, carbon or boron. And then the other thing that we can see is that you just go from having 1 to 2 to 3 unpaired electrons within these atoms. And then, of course, if you continue to oxygen, fluorine to neon, you're just putting in, one more electron, a second electron, and then finally a third electron into those particular subshells. So the neon configuration is shown here as being a completed 2p subshell. That's what's making our noble gases especially stable, is that they are just completing a shell with electrons, so that they don't need any electrons to fill their shell, and they also don't need to add any more electrons to complete their shell. So even though sodium has one extra electron in the 3s subshell, that's kind of the same trend of all of the alkali metals, is there's some sort of ns1 configuration on top of some completed noble gas configuration. So they're all sharing having just one valence electron. So periodic table, we can fill orbitals in increasing energy. The different blocks of the table correspond to different types of orbitals that are last being filled in for the atoms. So we have our S block, then our P block, and the D block, our transition metal series, and then this is where our F block could be wedged in. If you're not sure, you forget this, just look at the atom numbers from, say, the 5s, you end up over at the 4d afterwards for the next element, then you end up over at the 5p, then filling the 6s, then the 4f. Now, the numbers here, the thing that you might have to remember is the first P is a 2, so the first P block is a 2, the first D block is a 3, the first F block is a 4. So that makes this block the 5F. That means that this is the 4D, 5D, 6D. So you can get the numbers of the different subshells pretty easily if you just remember what the first block is in that particular group of elements. So the S and the P block are often referred to as the main block elements. So this is where you see your sort of, if you will, the main group chemistry. This is what you might call the transition metal group, transition metal chemistry, and this is your lanthanide and actinide series. So this is our more normal looking periodic table. So we usually put the F block here just to make the periodic table easier to print in a smaller amount of space. And so then you just have to follow along with the elements. You can look at the periodic numbers to see where the F block is wedging itself in, and it's between the 6s to the 4f and then 7s to the 5f. And then you can get the ordering just by following along with the periodic table. And so then you get the configurations for most elements by applying this thought. We do see that there's some variations in configurations, usually in this region of our periodic table. There's also some variations in the F block. There's no variations in the P block, no variations in the S block. And then there's like a couple in here that are also a little bit weird. So I don't expect that you'll memorize all of the anomalies, really any of the anomalies, but just that appreciate there are a few cases of anomalies in the transition metal series and then in the lanthanide actinide series. If you inspect a chart like this one, you can spot some of the anomalies. I'll just point a couple out in here. So we have chromium in the first row is anomalous in terms of its configuration, and so too is copper. If you look in the second row, there's actually a bunch. There's molybdenum, there's ruthenium and rhenium, there's palladium, silver. If you look on the next group of elements, tungsten's actually normal. Then we get platinum, gold are abnormal. If you look in the F block, I'll just point a couple out that you have a few like lanthanum, actinium. Notice how they're actually not the F1s that you might expect. You might expect lanthanum should have been a 4F1 and actinium a 5F1. They're actually D1s. There's a bunch in here too. So if you sort of inspect, you'll see a fair number of cases that are anomalous. Okay, so again, I don't expect you to memorize which elements have these anomalous configurations, but just appreciate that there are some in the transition metal series and in the lanthanide and actinide series. You can inspect the main block elements and see that they're all normal. The S block are also all completely normal, so it's worthwhile to see that we're not seeing any anomalies in the S or P block main group elements. So let's review the learning objectives for this chapter. So we should be able to calculate wavelength of electromagnetic radiation given frequency, or frequency given wavelength, just using C is equal to lambda nu. So that's our main idea here, is just being able to use the speed of light is equal to the wavelength times the frequency. The order of the different electromagnetic radiation, so know the order of, say, gamma rays are greater in energy than X-rays, which are greater in energy than UV light, greater in energy than visible, greater in energy than IR, than microwaves. And then the lowest energy would be the radio frequency, or the radio waves. You don't need to know the specific cutoffs, but I think knowing the visible is really worth knowing that that's about 400 to 750 nanometers, and so your UV is, the shorter wavelengths from there, and the IR is higher from there. Explain what photons are and be able to calculate their energies given their frequencies or wavelength. So photons are just the most indivisible forms of light. You can calculate the energy of a single photon using the expression h nu, or hc divided by lambda. So hc over lambda. Generally, h and c are your two givens on this exam in terms of fundamental constants. If for some reason you need things like mass of an electron, we would give you that. If you need to know certain equations, I'll point some of those out later, but equations that you generally are not given if you need them are these equations here. So these ones you should know, but also I think you'll come to know them pretty well if you just do plenty of problems. Explain how line spectra relate to the idea of quantized energy states of electrons and atoms. The one thing that probably is being skipped here is the objective of the photoelectric effect, just that one photon of light can interact with one piece of matter, be that a metal atom that's being ionized by a photon of light, if the photon of light has enough energy to ionize that particular atom, or if maybe that electron has enough energy to break a bond. So we're looking at bond strengths, maybe of things like O2, and finding complementary wavelengths to breaking that bond. So we can understand that one photon of light can interact with one piece of matter, and then one photon of light was being given off by one H atom changing its energy level. So we could see the idea that if you have some high energy state of hydrogen that's coalescing down to some lower energy state, then a photon of light can be given off in that process of one atom changing its energy level, one photon of light being created as a result. So that's all resulting from the photoelectric effect and the idea of quantized energy states. So we could calculate the the wavelength of a moving object. That's from the equation the wavelength lambda is equal to h divided by mv. And so this equation generally is actually given if you were to need it. And so if you need to plug into this equation, the thing you really need to know is how to plug your units in. There's an equation slide, so I'll talk about that a little bit later. Explain how the uncertainty principle limits the precision of which we can state the position and the momentum of subatomic particles. And so the equation is the one that looks like delta x times m delta v must be greater than or equal to h over 4 pi. And so this turns out to be an important equation for any piece of matter, but for the particles that happen to have high velocities and low masses, this is a much more important equation. So this is going to be a much more important equation for things that are behaving more quantum mechanically, like an electron. So you can see that for an electron, because of its relatively low mass and high velocity, that we're going to have this issue where we know from the previous example that the small particle can behave like a wave, but then it's also going to behave like a wave that we can't precisely know the exact location and velocity of the particle due to this fundamental limitation that falls out of quantum mechanics. And so this is going to lead, or led to the notion of orbitals as being a better description of a probability distribution of where you expect to find an electron, as opposed to treating the electron as a discrete particle. So treat the electron as a particle, but that is best described as a wave. Kind of almost the opposite of light, which is a wave that's almost better thought of as behaving kind of like a particle. So if we zoom in here, so relate the quantum numbers to the number and types of orbitals and recognize the different orbital shapes. So this is putting n and l together and the values of m sub l. So just that our limitations, or L goes up to n minus 1, the m sub L range is minus L to plus L, and then that the L is relating to the shape. So the L of 0 is S, 1 is the P shape, 2 is the D shape, etc. 3 is the F shape. Interpret radial probability function graphs for atomic orbitals. This is where we were looking at the 1s orbital has the greatest probability of being found relatively close to the nucleus. And then if you have a 2s orbital, then we have one of these nodes. And so we end up having one node for the 2s. And if you have a 3s, then you end up having a second node. So you have, so it looks more like that. So you have two nodes for the 3s. Explain, and you could also look at some of the P shapes are taking this sort of stage over here. So no nodes for like a 2p orbital. So a 2p orbital would have no nodes, a 3p would have one node, and these nodes being on the radius of the atom. So these are what we might be calling radial nodes within these radial probability diagrams. Explain why, how and why the energies of orbitals are different in many electron atoms from those in the H atom. So the many electron atoms have electron repulsions. So the electrons are going to be repelling each other within the atoms. That's going to cause their energy levels to be different. And so then for many electron atoms, this is where we get the idea of 1s to 2s to 2p in terms of the relative energy, then up to the 3s. So this is giving rise to the ordering of the elements in the periodic table due to the relative differences of the orbital energies. So draw an energy level diagram for orbitals in a multi-electron atom to describe things like the number of unpaired electrons. So this is like looking at something like, say, for nitrogen, having a 1s2, 2s2, 2p3 configuration. In terms of the way you might think of this diagram might be, thinking of the relative energies of these orbitals. But usually you end up just writing these just simply flat. So like if you write a 1s2, 2s2, 2p3 to get 3 unpaired electrons, a lot of times you just write these diagrams parallel, even though you're kind of picturing they all have a different energy. So it might be more common that we write diagrams like this, where it looks like all these orbitals have an equal energy, but really we just have to interpret that the 2p set of energies are all equal to each other, but higher in energy, the 2s equal but higher but not as high as the 2p, etc. So we can fill in our electrons just the same in a diagram that looks like this. So we're just getting and making sure we follow the Pauli exclusion principle, not putting two electrons into the same space, and a Hunds rule maximizing the spin when possible within degenerate orbitals. Then use the periodic table to write condensed electron configurations and determine things like unpaired electrons. I also think we need to determine like valence electrons is an important concept in this chapter too. So we need to be able to determine the valence count for atoms. So like nitrogen having 5 valence electrons, but 3 unpaired electrons is important to note from this chapter. And lastly, a summary of the equations from the chapter. C is equal to lambda nu. So important equation, already discussed that one. E is equal to h nu. These are two equations you just have to know. The Bohr model, we get there by taking hc, Rydberg constant, multiplying all three of these constants together. That's where you get the minus 2.179 times 10 to the minus 18 joules. I think that's a little bit more precise. I don't know why the book limits it just to 3 sig figs, but but you're just taking three constants, multiplying them together is where this value in joules comes from. And then you can use this to calculate a delta E. So if you ever need to do a calculation to calculate, say, a wavelength of light emitted from an H atom transition, usually you'd be given like an equation that looks like E is equal to minus 2.18 times 10 to minus 19 joules times 1 over the n value squared. And then you'd have to take the delta E for your E final minus E initial, work out your delta E, and apply that to calculating maybe a wavelength of light through the process, using perhaps one of these two equations here. So again, memorize the first two equations. You might be given the third if you need to do a calculation on a molecule using the Bohr model. The other two important equations are the de Broglie wavelength and then the uncertainty principle problem. And so these would generally be given if you need them, but the key is kind of knowing if we're going to get a wavelength out, what units do we plug in? So H is usually in units of joules times seconds. Now a joule is a kilogram meter squared per second squared. And then you multiply that unit of the joule times seconds. So we got to multiply this by seconds. So your fundamental units of joules times seconds is kilograms meter squared per second. And then we divide that by a mass in kilograms, and then a velocity in meters per second. If we use those units, then we're going to get out our wavelength of light in units of meters. So usually you have to convert it maybe to angstrom or nanometers or whatever units most suitable after the problem. So you might have to remember 1 angstrom is really small, 10 to the minus 10 meters. You might also have to remember that 1 meter has a bunch of angstroms, 10 to the 10 angstroms. So these are things you may have to just remember out of chapter 1 or 2, whatever the chapter was that we were mentioning, that particular unit. And then lastly, the delta X problems, and then the delta MV. Now, I usually summarize this as delta X, M delta V, since the mass is thought to be a constant here. So greater than or equal to H over 4 pi. And so delta X, the uncertainty in principle, that this is a value that should have units of length. It's the uncertainty in the position of an electron. So you're just kind of imagining an electron is behaving as a wave between two different particles. So it has some position M and then with some uncertainty. The delta M is the uncertainty. It's not really the change in position, it's the uncertainty in the position that matters, not the actual position. And then just like the particle at that point should have a velocity, so it's moving with a particular velocity with an uncertainty of how well we know that velocity, it's that uncertainty that matters here, not the velocity itself. So we're plugging in the uncertainty in the velocity in this problem and the uncertainty in the actual position. So let's use X instead of M. So let's say delta X here. So there's some position X plus or minus the uncertainty in that position, and the uncertainty is what gets plugged in here. And so anyway, so for delta X, our unit should go in units of length. So that's where the M comes from, the unit of length being the meter. The mass should go in units of kilogram. Uncertainty in the velocity should go in units of meters per second. H in our usual joules per second, joules times seconds. Okay, so that's our summary for chapter 6. Thanks for the attention.